Hey everybody, it's Tom Cherryholmes with the Linux MCE project, and I wanted to make a video showing the rewrite of the FujiNet CPM tools. While we will do some small walkthroughs of the tools, I wanted to actually concentrate on showing the process of how the tools are written and how they are compiled resident on the Atom themselves. And then we can see the entire build process putting this together and putting them onto a target diskette using the tools once they're built. I will make an aside here that you may be asking, especially if you already have a copy of the FujiNet tools for the for CPM Atom, why was there a rewrite? Well, the answer was quite simple. It was because the tools didn't work under TDOS at all. None of them. This included the network shell, nsh.com. So rather than leaving TDOS users out in the cold, I set to look for a solution to the problem. And the solution that I ultimately wound up doing was to use a different compiler. Instead of Z88DK, which I use for the majority of the Atom side of development for FujiNet, I'm using the BDS C compiler under CPM developed on the Atom. It generates code that works well on both CPM and TDOS. And it's very small, very compact. And the compiler is fast for it running on a 3.58 megahertz Z80 processor. The catch is that the code had to be rewritten, as BDSC does not support ANSI C. That means no C89, no C99, none of the modern conveniences that we find in today's C compilers. But instead, I had to revert to the first dialect of C, as put down by Kernighan and Ritchie. But all in all, it was worth it. It took about 2 weeks worth of work, and the result was quite nice, as you'll see here. We'll start by basically making a copy of the source code that's on Atom Apps here. It's inside the CPM folder, so we can go into that folder, and I can press the copy key. At this point, we can say that we want to copy it to my local TNFS file server if I wish, or I can put it on my SD card storage. I can then press the 6 key to perform the copy. It'll take a few moments for the copy to complete, especially because this is a 720K floppy image. I won't bore you too much with it here, but we'll take and pause it temporarily for just a moment. And we're almost done here. So with that, we wind ourselves back up at the host slot menu here, and we can subsequently mount what we've just copied over. We don't want a quick boot because this will mount it read-only. We want to mount it read-write. And the reason that I'm using a 720K disk is to provide not only the space for a bootable CPM, as well as a copy of the BDSC compiler and the libraries and things that it needs, but I also wanted to provide all of the source code and the necessary build scripts. Everything fits onto a single disk. We'll go ahead and boot into CPM here. And doing a little cursory examination, we'll see that we have about 438K free. What's on this disk is, as you can see here, the BDSC compiler, some libraries, some build scripts, as well as a few miscellaneous utilities such as sysgen, and a copy of a wonderful little shell replacement, or CCP replacement, called Microshell. And I love Microshell. I love it to death, even more than ZCPR. We'll go ahead and load it. It has a lot of fantastic features, and that would take an entire video all by itself. But the one that is very useful to us here is that it is much faster. It has built-in support for submit batch file processing, which is used for the build scripts, and that it processes each of those lines in the submit much faster than the standard submit utility. And it also has the ability to set so many different environment variables to configure the environment the exact way you like it. It offers search paths for utilities in multiple places, etc., etc., etc. And all these things kind of combine together to make one hell of a great environment to use inside CPM. For now, we'll take a little look at some of the bits and pieces of code here. You'll see that we have a mishmash of both tools for things like fmount, fhost, feject, etc. But we also have various library functions that the tools use, such as being able to find the DCB that's attached to a particular device. One of the things that's actually present on this particular disk is the excellent editor ZDE, and you can use it to look at a particular piece of software. Let's have a little look at the finfo tool. ZDE, finfo.c. And you notice I'm running this right off of the image. If you want to take and copy this to the hard drive, more power to you. It runs a bit faster. And you can see here we have all of this, just a small chunk of code here. All of this was developed here on the Atom in this editor right here. We went in and we built it. And then as I was building it, I would take and save the results. Oops. I will take and just quit because I don't want to modify anything. Go bye-bye. And then I would take and build the results. We would do so by calling the C compiler, which calls both pass1 and pass2 to generate an object file. But that's not complete. We can't run that yet. We have to link the object file that's created here with any additional library functions that might be needed, including the default C library function. And we will use the linker for that. And if we don't specify any particular libraries on the command line, such as strtoc and atomnet, it will ask us for them whenever it's time to link, which will happen here because there are a few functions that are not part of the default libraries. In this case, this program needs 3 of those functions: fdcb, wchdev, and rchdev. You'll see that these functions are actually part of a library which we call atomnet, and they are put together, as you'll see earlier. And actually, it looks like that's not here, so we'll actually have to build that. We'll go ahead and just build those functions real quick and just pull them in. First, we do fdcb, which finds the DCB in memory and returns a pointer to it. So we can get all sorts of information, such as how many bytes are waiting, the destination of the buffer in memory that we want to use, and device status, etc. Then we need wchdev, which means write character device. This is commonly used, for example, in the context of FujiNet to send commands to FujiNet. And you'll see here that even on this simulated floppy drive that's being run on the FujiNet, the compile time is acceptable. We need, conversely, our chdev, which reads from character devices. And this function is commonly used to grab responses, such as the received block or network information in the case of finfo. Now, with these three libraries written, we have a few CRL files that have been built here. We have def and def2, which are the default C library functions. But we also have finfo, which we built earlier, which still needs to be linked. And we have fdcb, wchdev, and rchdev, which we just compiled. Let's invoke the linker to see if we can finish up finfo here. And again, I'm going to not specify any of those libraries on the line so that we can take and resolve them by hand. And I did fdcb. You'll see wchdev, rchdev, and I'll hit return to try searching through the standard libraries for peak because I know they're in there. Finally, we see that we're successful. We wind up with a few bits of statistical information about the size of our binary. But we also have a COM file ready to be used. And if we run it, we see our FujiNet network information. All right there, ready to go. With that pretty much leads us, okay, the next thing that we really should do is to try and combine those FujiNet network information bits together so that they can be used as a single library and we don't have to take and put in those individual functions. Each time we can just point it at the library and the linker will do all the work. For that, we'll use the clib here, which is the librarian. And this has its own command line here. We'll start by making our AtomNet library. This creates an empty library that we have to take and put things into. We'll go ahead and open it up to file number 1. Files are numbered 0 through, I think, 15. So we want it to be the destination, so by convention, I use channel number 1 for this. We'll go ahead, open it up, get it ready. So good so far. And we'll start with fdcb. Open that in channel 0. We'll transfer from 0 to 1, and we will transfer all the functions. There's only one in here, but it does it nonetheless. We can then close 0 and do the next one. And we will do the same for wchdev. And close 0. And the same for rchdev. Now we can go ahead at this point and have a list of the files that are of the individual functions that are in the AtomNet library that we just did. We can see that we have these functions in here ready to go. And we're done with this library now, so we can close 1. It will take and do all the housekeeping needed to crunch the library up into a usable form and return us to the command prompt. We can then quit. Are you sure? Absolutely. At the same time, now, instead of having to specify each individual function library separately, and so on, we can instead do this. And C-Link will automatically pull the functions out from the library that we've put together, making it a bit easier to deal with, especially if you're building submit scripts. But now that we've kind of shown the basic process of what happens here, we can then take and turn our attention to a couple of submit scripts. We have a couple. We have build, which builds everything. We have clean, which does the opposite. It cleans everything up and puts everything back the way you got it. You also have copy C, which will copy BDSC and all the bits and pieces that it needs onto a fresh floppy disk that you specify. So you can use it as a compiler disk or whatever. And finally, you have a simple submission script that runs CC and C-Link for you with the AtomNet library already there. Useful, perhaps. So, with that, we'll take a quick look at the build sub, and then we will run it. You'll see right here that it is essentially all of the individual commands that we would normally run by hand, typed into the submit file, run one right after the other. There's also an xsub command here. We use xsub because we need to go inside of the C librarian and issue commands from inside of it. And you'll see the same commands that I gave before are present inside here, inside the submit script. After we're done, we kind of clean up the intermediates with erase, and then we start building each tool, one right after the other, ending with cleaning up the intermediate link files that were created in the first place, and signaling that the build is done. We can see this in action in Microshell by turning on the verbose function here. And we can immediately take and start the build. On this particular atom, on this particular disk image, it takes approximately 10 minutes to complete the entire build. And I'm going to spare you from that and basically pause until it's finished. I'll go ahead and interjection in the middle here. You'll see that through xsub, we've called the C librarian, and we're calling all of the commands that you saw me type manually inside of the librarian so that the AtomNet library can be built. And now we're almost done building the network shell, which is the last major component. Right down there at the bottom of usable memory. Yay! Second pass. And finally, the link. Since the NSH has a string tokenizer and BDSC didn't have an implementation of string token, I kind of cobbled one together. See there. Give it a few moments, and we'll have the last binary. Okay, everything there, all good so far. We clean up all the intermediates from making all the tools, and the build is done. Okay. What does that leave us with? Well, it leaves us with all our source material and all of our COM files, which we can subsequently take and copy over to our new space. Let's use our new tool here to take and make a new disk. We'll go ahead and make it on my ENFS file server here locally. And we'll simply call it tools.dsk. It's a DSK. It also needs to be 720K a piece. We'll put it in slot number 2, and it will create the disk. Takes a few moments. As it's creating the disk, it's actually going through and filling the disk up with E5s so that it can already be used for CPM. Boom, we're done. It's ready to go. And we are presented with a nice fresh disk, which if we do a stat on, you'll see that stat's not on drive B, but because Microshell works the way it does and it has a search path, it searches for stat.com on drive A. You can also do this to search on your RAM disk as well. So we'll go ahead and use pip to copy the tools over. And there we go. We have our little tool disk here that we can use. So with that, I think I'll end the video here. I wanted to kind of just show a bit of putting together the tools, how they all fit together, and the reason why I spent time to try and make all of this work in multiple operating systems. And actually, as a matter of fact, I did tell you that it did work under TDOS, right? Yes, I did. Let's wait for this to finish, and then we can take and boot TDOS. But even here, you've seen here that we've built the tools, and then we've made a new disk with those tools and copied the resulting tools onto that disk without having to reboot the FujiNet to go back into config. Okay, so with that, we'll go ahead and I will hit the reset on the FujiNet, boot back into the FujiNet real quick, and I will switch to my Atom IDE hard disk image, which will inadvertently put me in TDOS. I'll go ahead and boot this. And we see that we're now sitting in TDOS. Get rid of the function keys. And I've put my environment over here on drive C. And there's a copy of BDSC that's in drive B. And I've configured BDSC appropriately to let it know that that's the case. And because of that, I can essentially do stuff like this. I can go ahead, I can edit something. Come in, make a change, do whatever. And then I can take and build that change. on the hard drive. I can test it and see that it works. And all of the tools work just as well under TDOS as they do under CPM. We can, for example, go ahead and go to my EFS here, mount the disk that I just made. I'll do it read-only. And go to drive F. And there it is. So with that, I'll go ahead and end the video here. I hope you guys have found this informative. And again, I'll be making more videos now that things are starting to come together and the firmware is really starting to firm up. But don't ever forget, the FujiNet is 99% a software platform. So as features come online, you do a firmware upgrade, you get the new features. There's actually very little, if any, hardware that actually changes between revisions. So with that, that's it for now, guys. And as always, until next time, have fun.